We're talking about the other functions that are necessary for this course. Okay, we've done linear functions, quadratic functions, exponential, logarithmic. You will soon do circular functions, which deal with sine, cosine, and all those good ones. But before we get there, we need to cover the last of the functions, which are your other not so common functions, like your absolute value, your modulus functions, and just a few other ones. So this is going to be something that I don't think you guys have seen in any other class. The absolute value ones you probably have seen, but we're probably going to do some stuff with them that you've probably never done with them before. Okay, so to start off, even and odd functions. Now this should be reviewed. This should be a review from pre-calculus. Okay, but even an odd function, if a function is even, it's when you basically plug in a negative x in for every x into a function, and you get the original function f of x. Okay? If you do have an even function, that means it was symmetrical about the y-axis. Okay? Do y'all remember that? And then if a function is odd, again, you take negative x, you plug it in for every x in the function, and then if you get negative f of x, then it was an odd function. If it's an odd function, that means it was symmetric about the origin, not the x-axis. That's incorrect. Okay? So in other words, symmetry. Okay? If it's an even function, it has y-axis symmetry, which means you could fold along the y-axis, and the left side of the function matches up to the right side of the function. Your most prime example of an even function would be x squared. Odd function, if it's symmetric about the origin, that means you could basically take one half of it. If you reflect it over the x-axis, reflect it over the y-axis, it basically one half will lie right on top of the other half. Your most basic odd function would be x to the third. Okay, so here's two examples. This one here is an even function. Okay, algebraically, if I plug in negative x for every x into the function, that will give me a negative x that needs to be squared, that quantity squared. Of course, a negative x times a negative x is a positive x squared. Hence, you get the original function. So because you get the original function, it's even. And then, of course, you do the similar process for this other function. A negative x times a negative x times a negative x is a negative x cubed. This entire function is negated, okay? That is that f, that negative f of x. So the original function is being negated, hence why it is odd. Okay? Yes, these are basic examples, but that is the process to go about even and odd, or determining if the function is even or odd. Y'all remember? Okay. Well, then what I want you guys to do is I want you to determine this one. You can do this on your desk. Okay, I want you to determine whether each function, a, b, and c, even, odd, or neither. Okay? So, again, to determine if a function is even, odd, or neither, we're going to plug in negative x for every x that we see in the function. So when you did this, hopefully you recognize that just because the denominator has a negative x in it, that makes the entire fraction what? To make the entire fraction negative. And this is the complete opposite of the original function, so this one was very good. Over here, you're doing the same thing, plugging in negative x. Please be very careful. Make sure that you're raising a negative x to the fourth power and a negative x to the second power, which becomes what? And this is the exact same, so that means that this one was even. Good stuff. Over here, you're doing the exact same thing, plugging in negative x. This time was negative x squared. Positive. And then you'll have negative 2 times negative x, which becomes? And then you have a plus 3. Exact same, exact opposite? No. So this one was a neither. Who's 3 for 3? Raise your hand. Okay, good stuff. So yes, please make sure that for it to be the exact opposite, every single thing will need to be different. Will need to be changed. Okay? We're going to do this one together. The next one's going to be on your own. It says to prove that the sum of two odd functions is also an odd function. Okay? So it says prove that the sum of two odd functions is also an odd function. Well, in order to do this, that means we need two functions, right? F of x and g of x. We're trying to see if the sum of these two functions, which will give us one function, is the sum of two odd functions is actually going to give us an odd function. So we need basically two functions that are added together to start with that produce another function. Okay? This is in the general sense. We're not given an x squared minus 2x plus 3. We're talking about in the general sense. Okay? More specifically, we're talking about two odd functions. So if I add two odd functions, will that produce an odd function? Or actually it does. We're just trying to prove it. So, in order to determine if a function is odd, what do? We plug in negative x, and then the result should give us a what? Okay, and so when I do that for this particular function, if I plug in a negative x into f of x, and it's supposed to be an odd function, what should I get as a result?
Negative g of x?
No, negative.
I mean f.
Yeah, negative f of x. Okay, so I have an odd function. Okay, plug in negative x. If it's going to be an odd function, I should get what here? Negative g of x. And so a plus a negative becomes a what? A minus. Okay? Now the thing is that this is supposed to produce an odd function. So, you see how both of these have a negative in common? What can I do with that? You can factor out that negative 1. When I factor out that negative 1, what does that give me? And what was f of x plus g of x? H of x. So now you have negative 1 times h of x, which is just negative h of x. Isn't that the exact opposite of the original? Therefore, questions on this?
So you were just so they gave you h of x, and they said h of x equals the function f of x plus g of x.
No, I did that because I had to prove that two odd functions is going to produce an odd function. So I started with the sum of two functions equaling a different function. Okay, so I basically needed to show that this, once I added two odd functions, was going to produce the exact opposite. So I had to basically create these as odd functions and then algebraically get to the process where it was the exact opposite of the original function. So that first line, that was not given. That was something that we created based off the fact that we had the sum of two functions needing to produce another function. More specifically, two odd functions producing an odd function. Okay? So using that, I want you guys to try this one. You're proving that the product of two odd functions is an even function. You can start off the same way we started the other one, just make sure that you're using the correct operation. So, this time, we have two functions that are the product of two functions is odd. How do I represent that? Product. That's multiplication, g of x, okay? Yes, the binary x, don't use the dot. The dot represents something completely different. You'll learn about that next year, okay? So use the binary x. We have two odd functions, which means we need to have these two functions to both be negative. So I have a negative f of x times negative g of x. A negative times a negative is a positive. So then that gives me f of x times g of x, which is the original h of x, is it not? So h of x does indeed equal h of x. Therefore, h of x is even. Does my work differ from your work? Okay. Well, I mean, not really, but like, does it differ? Okay. Questions on even odd functions? So I'll give you something else specific to a actual function, something in general. We okay? special functions, okay? So we have the graph of y equals f of x, a function that quantity squared, okay? There are some key features of these types of functions, okay? The points with y coordinates 0 or 1 are invariant. That basically means that they don't change, they stay constant to what they are. The graph of this function touches the x-axis at its x-intercepts. This function lies above or on the x-axis for all x's, okay? And that would make sense. If you square a negative number, if you square a y value, whether it's positive or negative, it's always going to be positive, which means that those y values are going to be above the x-axis. Remember, f of x equals y. So if we square your y's, that means that all of them are going to be above the x-axis anyway. The vertical asymptotes of any function of y equals f of x are also vertical asymptotes on that function squared. Okay? So if you're given a function and it has vertical asymptotes, well then, if that same function, it being squared, are going to have the same vertical asymptotes. See that some stuff got cut off, so let me move it up real quick. Bless you. Okay. So I'm going to have to... when your function's y values are between -1 and +1, then the function squared, the graph of that, is going to be closer to the x-axis than the original function. And also when your y values, absolute value of your y values is greater than 1, then on the function squared, it's further away from the x-axis than the original function. The first graph, the second graph, B, that's the one that we're going to do together. And then I want you guys to try the other three on your own after we do this. Okay? So let's go through the features real quick, okay? It says that the points on the y coordinate 0 or 1 are invariant. Again, that means they don't change. As we look at this graph, we can see that the point that's on our y, we don't have a y coordinate of 0 or 1. All right, the next one says it touches the x-axis at its x-intercept. So that means that when we graph the square function, it is going to touch the x-axis where the original graph touched the x-axis as well. It needs to lie above or on the x-axis for all your x's, which means that this part right here that's below the x-axis needs to be above the x-axis, okay? Everything else will stay above the x-axis because that's where it is, but because, again, we're squaring, that means all your y values are going to now be positive, okay? Let's see, we don't have any vertical asymptotes, so we don't have to worry about that, and we also don't have to worry about it being closer to x because it's not like there's anything that's in between, like how I showed you with like an exponential or like a rational function. Okay? So pretty much all we have to do for this one is we have to take care of the fact that it goes below the x-axis here. Okay? Now we are given a point, which is -1, +2, or sorry, -1, -2. And we know that with the square function, this means y. So when we square it, what's going to happen to that y value when we square it? Positive what? +4. So when we plot this point, it needs to be located at -1, +4. Okay? And it's still going to have that quadratic parabolic shape to it between -3 and -1. Okay? So far, so good? So we are still curving, but we have positivity in between -3 and +1, and we continue to curve up following the graph. And what you see in the blue is our function squared.
So because it can't be below the x-axis, that's why it had that.
Exactly. So it's almost like what's that word that bounces? It basically bounced off your x-axis.
Do we always have to follow the actual curve?
No, as long if it's increasing, then it should be increasing, or if it's decreasing, it should still follow suit.
So I don't have to like go over where the original function was.
Correct. Questions? Okay. You guys try. All right. You guys give it a try. Let's try A and C. Okay. And just make sure you guys are good on A and C before you guys do 2. Okay, which is this one down here. All right, let's see how we did. Now remember, it's asking you to graph f of x squared. Okay, so one thing you definitely should keep in mind is that these graphs should have some type of curvature to them. Okay, not linear functions or anything like that. So should have some type of curve to them. Okay, as we can see for first one, A is hitting the y-axis at 2, has an x-intercept at 3, so we know we definitely have to stay at 3. This part that's down here needs to come above the x-axis, and on top of that, we should hit the y-axis at what value? 4, because again, we are squaring our y's, okay? So it needs to go through 4, it needs to bounce off 3, and this part needs to be positive. So you should have some type of almost some quadratic looking shape. Yes? Okay? And remember, those values that are in between -1 and +1 should be closer to the x-axis than those other values. So at some point you should go below that line when you're doing your curve. Okay? All right, let's look at the other one. Okay, now this one does have an absolute value. Okay, so let's kind of go back through our properties. Okay, we don't have any x-intercepts. We don't have any y-coordinates. There's 0, 1. We do have a part that's below the x-axis, so this whole part here is going to need to come above the x-axis. We do have a vertical asymptote, and as the property said, vertical asymptotes on the original function are also vertical asymptotes on the squared function. So this still holds true for our squared function. Okay? Any values that are in between 0, 1 needs to be closer to the x-axis than the original function. So at some point in time, the curve that's going to be on the right side of this vertical asymptote should be closer to the x-axis. Did you draw that? Okay? Still holding true to your horizontal asymptote as well. And then this gray part here is going to need to be above the x-axis. It does have a y-intercept at -3, so where should the y-intercept be on the square function? +9. So at some point you should hit 9 on your y-axis. Okay? Yes? Okay. Now this last one, okay, it said for the graph you actually need to sketch that function squared +1. So you need to take care of the squared part first, and then after you do that, what should you do? You should move it up 1. Okay? So take care of the squared and then move it up. All right. So in this tan color, I'm going to do just the squared part. Okay? Because then once I have the squared part, all I gotta do is move everything up 1 unit. Okay? So when I take care of the squared part, I know I still have an x-intercept at -1. This y-intercept needs to be where? Just the squared part.
1.
It needs to be a +1. Okay, this asymptote can't be a -2 anymore. It needs to be where? It needs to be a +4. Okay, and so then when I do my curve, this is what I should have. Okay, almost treat this kind of like a reflection-ish, kind of. Okay, questions?
How come it goes through the
Yeah.
You can jump.
Or does it have a hole?
No. This part still stays true to everything. Yeah, it's the end part that's taking care of that.
That's 5, right?
Well, yeah, but this is just the square part.
Oh,
Yeah.
okay, never mind.
Okay, so that part still needs to follow, the end part still needs to follow an asymptotic behavior with that asymptote there.
So that beginning part isn't.
Mm-mm. Yes, that asymptote does not apply to that part. Okay. Now, in the red is my final answer. From here, I just need to move everything up. This is now going to be at +1. This intersection is going to be at +2. And my asymptote is now going to be at what value? 5. So, the red is your final answer. Okay? Questions? Let's keep going with some other functions, okay? This function, the graph of y equals 1 over f of x, okay? Very similar to your rational function. So we kind of talked about this a little bit, but we'll talk about it a little bit more in detail, okay? Some key features of these types of functions, okay? Zeros on your original function now become vertical asymptotes once you changed it to 1 over your function. Vertical asymptotes of your original function now become zeros when you do 1 over your function. Local maximum of your original function become local minima of your 1 over f of x function. And vice versa. Local minima become, on your original, become local maxima on your 1 over f of x function. This is nothing but a reciprocal. Okay? It's nothing but a reciprocal function. A few more features. Okay? Which make sense if you think about it. When your original function is, when your y values of your original function are greater than 0, the same is going to happen for your reciprocal function 1 over f of x, okay, and vice versa. When f of x is less than 0, 1 over f of x is also going to be less than 0. So in other words, if your y's are increasing on 1 over f of x, your y's are still increasing. That hasn't changed. And then and when your y values are greater than 0, it's still going to be the same thing. Pretty self-explanatory. So nothing weird about the behavior of the ends of your graph. Okay? So in your calculator, I want you to graph in y1, x squared, x, and then in y2, 1 over x. Okay? So in your graphing feature, I want you to graph x and 1 over x. Okay, for right now, we're just taking a look at these graphs here. Go ahead to a standard window so you can see. Okay? Anyone have this graph? Yes? Okay, so just real quick, just look over the properties. Okay? Any zeros of the original function become vertical asymptotes. Okay? When you do 1 over that function. All right? And as you can see there, at that 0, 0, there's now an asymptote there. Okay? We didn't have any vertical asymptotes on our original function. We didn't have any extrema either. And we can see questions? Would you be able to graph this without using your calculator? Like if I gave you, this is a simple one.
Teachers and students, pardon the interruption. If you would release the tour guides for...
Even though y equals x and y equals 1 over x, they're your basic parent functions, I'm pretty sure that if anything, could always fall back on your knowledge of graphing them. But I want you guys to see, if anything, the features and how they're similar for functions that you already know. Because when I give you just any old random graph, you should be able to graph its reciprocal. Okay? So remember, any zeros should be vertical asymptotes. Any vertical asymptotes should be zeros. Any extrema, any maximum should be a minimum, and vice versa. Okay? So when I look at the next one, you guys should already have it in. You should be noticing these different features. Yes? Please make sure that if you do not use the fraction feature and you're just typing it in straightforward, please make sure you include parentheses around that x squared. I wrote it that way on the board for you, so then that way if you do decide just to type it in regularly, you do include the parentheses so you can get a function there. Okay? You can't see it that well, but you guys see how it kind of goes up right there at your y-axis? So there is a minima here, so there should be a maxima. Okay? And if you think about it, the minima occurs at 0, 4, when the y value is 4. So when you do the reciprocal, it should be at 1/4. So that's why it's so small. Like if I were to zoom in a little bit, I would see that it would rise at 1/4. Okay, so you know where the maxima should occur. Okay? Let's look at the last one. Okay? Type that one in. X squared plus 4x plus 3, and then 1 over that function. So x squared plus 4x plus 3, and then 1 over that function. You see your observations? X-intercepts are the vertical asymptotes? Yes? Do you have any extrema? Is the opposite on that reciprocal function? So I have 2 x-intercepts, so I should have 2 asymptotes, which I do. You guys see that? Okay? So anywhere where there's an x-intercept, there should be a vertical asymptote on your reciprocal function, which there is. Again, any x-intercept, there should be a vertical asymptote, which there is. The blue represents the original function. The red represents 1 over that function. Okay? There's a minima on your original function, so there's a maximum there. Okay? Questions? I'm having you guys look at a few of these, so then that way when I give you some, you're going to be able to graph their reciprocals. Okay? So I want you guys to give these a try. Okay? These will clearly be without your calculator because you don't have a function here. But using those other features, I want you to graph the 1 over f of x function. Make sure you look at some key features on each of those graphs. X-intercepts, any asymptotes, max extrema. Okay? Just check with this first one. I know some of you guys are still working. Let's check with this first one, though. Remember, wherever there's an x-intercept, what should you have on your reciprocal function? An asymptote. So I should have an asymptote here. And I should have an asymptote here. Do you guys have that? Yeah. Okay. Wherever there's a minima, I should have a maximum. Okay. So I need to have a maximum. And where should it be, though? Should it be at that same point? It should be at -1/2. So still 1 1/2, but I should be at -1/2. So it should occur here. Okay. And it needs to be a maximum. So I still need to follow my rules with the asymptotes. So I get vertical asymptotes. I get very close, but never cross or touch. Okay, what's going to happen on the left side of this left asymptote?
Does it not cross the y-axis? But it's like on the,
It won't cross the y-axis, no, because there's asymptote there.
and it's like vertical, or it's positive.
It is positive, so all the y values are positive. Do I cross the x-axis at all?
No.
Nope. What about on this side, on the right side of the right asymptote? Goes down. Similar fashion. Do you still need more time, or you guys have B and C?
More time.
More time? Okay. So with B, wherever there's an x-intercept, we should have a vertical asymptote. So we have one x-intercept, so we should have a vertical asymptote at the y-axis. Do you have that?
Yeah.
Good. Now wherever there's a vertical asymptote, I should have an x-intercept. So I do have one here, so I should have an x-intercept at 4, 0. Do you have that? Okay. Now I do have a horizontal asymptote. Okay, so I still need to kind of hold up the laws of the horizontal asymptote. Is the horizontal asymptote going to change its location, though? No, it's still at 1, because think about it. 1 over 1 is still 1, so it's still there. Okay? And it is a reciprocal function, so you have flipped your pieces. So this part that is there on your original graph should now be where? It should be going to infinity as it approaches that asymptote, yes? Okay, it should basically be above in this general area. And these other pieces, the part that's on the right side of that pink vertical asymptote, it does need to go through my x-intercept, okay? Questions? Let's do this last one. I have 3 x-intercepts, so I should have 3 vertical asymptotes. I have a maxima here, so I need to have a what on my reciprocal function? Is this location going to change, or is it going to still be a negative 1, 1? It's going to stay there. So there should be a minima here. So following the rules of a vertical asymptote. I have a minima on my original function at 3, negative 2. So I should have a what where?
Maxima 3, negative 1/2.
3, negative 1/2. Very good. Maxima. Okay. What's happening on the left side of that far left asymptote?
Does it like not touch the x-axis?
It doesn't touch the x-axis. Is the curve going to be above the x-axis or below the x-axis? How do you know?
Because the original function is negative.
Very good. Yeah, because those y values are negative, so 1 over a negative value is still negative. And then what about on the right side of that far right asymptote? Positive, and it should not touch the x-axis either. Questions? Questions on the reciprocal functions?
What?
Alright, let's move on to your modulus functions, your absolute value functions, okay? Alright, your absolute value functions. Okay, we have the absolute value of a function, f of x. You have the original function, f of x is greater than or equal to 0. And you'll have your negative f of x function if your function is less than 0. Okay? Some key features. You want to make sure that you keep the graph of f of x greater than or equal to 0. Okay? Reflect the graph over the x-axis for any f of x values that are less than 0 and discard what was there. And then the points on your x-axis, so any point that's on your x-axis are invariant. In other words, they don't change. Okay? Now these types of functions, these ones are, I would say, easier than your squared functions because you have to think, it's your modulus, it's the absolute value, okay? Y'all remember what the absolute value function looked like?
No.
It looked like a V. Okay, so your ends are going to be straight. You're gonna have some straight points at some point. Okay? Or not so much straight points, but more so like you're gonna trace over the graph for these types of functions. Unlike your square functions where you made the curve wherever as long as it was still like in the same general area as the other ones. But for these, you're actually gonna trace for any part that's above the x-axis, you're gonna trace over the original function. But then of course any values that are below your x-axis, you need to make them positive, hence the modulus, absolute value. So then those will be above the x-axis. Okay. Modulus. IV's absolute value. Okay? Just like gradients or slope. There's some other things too as we come across. Alright, so we're gonna look at a few examples to think. Now we're gonna do another set of notes and then we'll look at some examples. Okay? There's a difference when you have the modulus just around the x, not around the entire function. Okay? So the graph of y of f of the absolute value of x. Okay? So if you want to compare the two, the first one, the one on the other slide, was the absolute value of basically your y's. This is the absolute value of your x's. So we know that, first of all, we know that the absolute value of x basically means that, x if x is greater than or equal to 0, negative x if it's less than 0. So for f of absolute value of x, you see what you see on the board in the black. Key features of these graphs, you discard any part of the graph that's where x is less than 0. You reflect the graph of x is greater than or equal to 0 over the y-axis and keep what was there. And any points that are on your y-axis are invariant. So in other words, if you have any point that's on your y-axis, that point does not change. Okay. So they have some distinct features. And what we're going to do is we're going to graph several of these so you can get some practice. Lots of graphs. That's probably what we end with today, and then we'll get more into modulus on Thursday. You guys going to be here on Thursday? We plan on it. All right. So we're going to do this example together, these two examples together, and then I want you're going to try one on your own, okay? So we're going to draw the graph of f of x equals 2x minus 4, and then on the same set of axes, we're going to graph the absolute value of f of x, and then f of the absolute value of x, okay? So please try to make your graphs of the original function at 2x minus 4 the best possible graph. So then that way, when you do the absolute value ones, they're pretty clean. What does 2x minus 4 look like? What does 2x minus 4 look like? And y-intercept at -4 and then increasing by 2. What do you mean?
Like up to over 1 for every x.
Okay. So in other words, it forms a.
Slope of 2 or greater than 2.
And what shape is this? What figure is this?
A line.
A line. Yes. So we have a line. Okay? We have a line. Try to make this as nice as possible. Okay. So now we need to graph y equals the absolute value of f of x and y equals f the absolute value of x. Okay? So let's start with the absolute value of f of x. So remember, it said that we need to keep the graph of f of x greater than or equal to 0. We reflect the graph over the x-axis for any y values that are less than 0 and disregard what was there. And any points that are on the x-axis don't change. Okay? So any point that's on our x-axis doesn't change, so this point is still there. Any points that are above the x-axis, okay, we keep those the same. So all of these that are above the x-axis, we keep those the same. Okay? And any points that are below the x-axis, they need to be reflected over the x-axis, and we get rid of any part that was below it. So all of this part that was down here, it needs to be now above the x-axis, so we need to reflect it. So that means that we're going to have a y-intercept not at -4, but where? At +4. And there is the modulus of f of x. Questions? Now you can do the f of absolute value of x on the same graph. You have different colors. Me, I didn't want to put it on the same graph because I didn't want to confuse. Okay? So I'm going to do same thing, just I have it on a different graph, but you can do it on the same graph. So now it says you discard the graph of x is less than 0. Okay? So any x values that are less than 0, you got to get rid of them. Okay? And you're going to reflect the graph of x is greater than or equal to 0 over your y-axis and keep what was there. The points on your y-axis are invariant, so they don't change. So that means that any point that was on your y-axis doesn't change, so that point of 0, -4 stays the same. I need to get rid of any part of the graph where the x values were less than 0. So these points right here, where the x values are less than 0, I got to get rid of that, so I'm not going to have that. And I'm going to reflect any part of the graph where x is greater than or equal to 0 over the y-axis and keep what was originally there. So in other words, this part stays because that was what was originally there, but I also need to take this part and reflect it over my y-axis. So this point that was at 1, -2 is now going to be at -1, -2. This point that was at 2, 0 is now going to be at -2, 0. And this point at 3, 2 is now going to be at -3, 2. And then that's going to be what you see in the purple, f of the absolute value of x. That was using all those 3 key features. Does this make sense?
Yes.
Okay? Y'all want? Well, it's not really an option. Y'all are going to practice. Yes?
Can you ask us and can we say yes?
Need to practice?
Yeah.
Okay. All right. So let's graph this one. And the thing is, we gotta make sure the original graph is right before we try to do anything. So I'm gonna do the original graph with you just to make sure everything's okay. What kind of a function does this look like? It is a quadratic, and it's in X-intercept form, so that means I should have X-intercepts where? 0 and -2. And that means, does it open up or does it open down? Opens up. Where is my vertex? That's the y value. What's the x value? -1. Don't forget, it has to be halfway in between your x-intercepts. So -1, that's where your x-coordinate is, and then you plug in -1 into your function, you get the y-coordinate, which is 2. And it does open up. So we have So here's our function, okay? So what I want you guys to do is you need to graph absolute value of f of x and f of the absolute value of x. All right, so let's start with the purple, okay? So we know that for the absolute value, the modulus of f of x, we need to keep the graph of f of x is greater than or equal to 0. So anything that's above, we need to keep it the same. Yeah? Okay. We're going to above, we need to keep it the same. And then anything that's below needs to be reflected. We need to get rid of it. So all of this that's below needs to go. And x-axis points stay the same. What did your graph look like? Look like a W?
Yes.
Yeah? So it didn't like curve? Was it a curvy W, like in the middle? Or was it like a straight edge W?
It was pretty sharp.
Pretty sharp? Okay. So, remember, this is still turning these y values positive, so you still need to have a curve there, okay, to represent this. So this one would be here, this point would be here, but it still needs to curve, okay? However, these can stay how they were. There. What about the pink? Anything that's below, anything that's less than 0, any x values that are less than 0, they have to go. So basically, a majority of this graph is gone, and the part that is above, or that is greater than 0 needs to stay, and what do I need to do with it? Reflect it. So that's what it should look like. Questions? All right. So we'll stop there, and then we'll finish up the rest next class. But make sure you are aware of those key features of those different types of functions when you are graphing these other functions.